even in a cosmos stretched beyond counting, where galaxies spiral outward like scattered seeds and time folds back upon itself in ways no mind can hold. There has never been another arrangement of atoms quite like the one breathing here, now, in this body, with these particular memories and half-forgotten dreams. The mathematics of infinity, strange as it seems, does not promise repetition, only endless variation, endless becoming, endless difference. And somewhere in that vastness, a single thread of consciousness emerged that could only ever be you, unrepeatable, irreplaceable, woven from moments that will never align again in quite this way. If these quiet hours bring rest, perhaps leaving a subscription might carry more of them into future nights. The universe, in all its immensity, made room for exactly one of you, and here, gently, is where that story unfolds. When you wake on an ordinary morning, in that soft interval between sleep and full awareness, something quite remarkable is already underway, though it feels as familiar as breath, as unremarkable as the pale light filtering through your curtains. Your body, warm beneath the covers, is not simply resting there waiting for your mind to catch up. It is, in fact, a symphony of staggering complexity. 37.2 trillion cells working together in quiet concert, each one performing its designated tasks with a precision that would humble the most sophisticated machinery ever constructed by human hands. This number, 37.2 trillion, is difficult to hold in the mind, and perhaps that is just as well. For if we could truly comprehend the scale of activity occurring within us at any given moment, we might find it rather difficult to ever fall asleep at all. Within the soft grey matter of your brain, approximately 86 billion neurons are engaged in their ceaseless communication, sending electrochemical signals across synapses in patterns so intricate that neuroscientists have spent entire careers mapping just tiny portions of this vast network. Each neuron may connect to as many as 10,000 other neurons, creating a web of potential pathways that exceeds the number of stars in the Milky Way galaxy. And yet, here you are, perhaps still drowsy, perhaps reaching for a glass of water on your bedside table, entirely unaware of the computational magnificence required to coordinate even that simple gesture of arm and hand and fingers closing gently around cool glass. The story of how science came to understand the instructions that build bodies like yours is itself a gentle tale of accumulated knowledge, of patient researchers working across decades and continents, each contribution adding to what came before. In 1953, at the Cavendish Laboratory in Cambridge, two scientists named Francis Crick and James Watson, building upon the careful X-ray crystallography work of Rosalind Franklin and the chemical insights of many others, proposed a structure for the molecule they called deoxyribonucleic acid, the now familiar double helix that would come to be recognized as the carrier of hereditary information. This discovery, announced with characteristic British understatement in a paper running barely more than a page in length, opened a door that would take another half-century to walk through properly. The Human Genome Project, that grand international collaboration, reached its essential completion in 2003, revealing that the instruction manual for building a human being consists of approximately 3 billion base pairs, Those chemical letters we represent with the abbreviations A, T, G, and C, arranged along the twin spirals of your chromosomes in sequences that somehow encode everything from the color of your eyes to the particular way your immune system responds to a novel pathogen. 3 billion is another number that slips away from intuition. And perhaps it helps to imagine that if you were to read aloud the sequence of your own genome, 1 letter per second, without pause for sleep or sustenance, the task would occupy you for approximately 95 years. Your entire genome, the complete set of instructions that specified how to construct the particular body you now inhabit, fits inside the nucleus of nearly every one of those 37.2 trillion cells, coiled and folded with exquisite efficiency into a space measured in millionths of a meter. But the materials from which your body is made, the actual physical atoms that constitute your bones and blood, and the soft tissue of your brain, these have a history far older than any genome, far older than life itself. Every atom of carbon in your body, every atom of oxygen and nitrogen, and the trace elements that your enzymes require, was forged in the hearts of ancient stars that burned and died billions of years before our own sun ignited. The calcium in your bones was created in the explosive death throes of stars, vastly more massive than our own, scattered across space in supernova remnants that eventually coalesced into the molecular cloud from which our solar system formed some 4.6 billion years ago. The iron that gives your blood its ability to carry oxygen was similarly created in stellar cores, under pressures and temperatures that make the interior of our sun seem almost gentle by comparison. Carl Sagan, the American astronomer whose gentle voice introduced so many people to the wonders of the cosmos, put this rather beautifully in his 1980 television series called Cosmos. He observed that we are made of star stuff, that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were all made in the interiors of collapsing stars. This is not poetic license or metaphorical flourish, but simple physical fact, the kind of fact that becomes more astonishing rather than less the more carefully you examine it. The atoms in your left hand may have come from a different star than the atoms in your right hand. And the atoms that you will breathe out with your next exhalation may find themselves, millions of years hence, incorporated into living beings on planets orbiting stars that have not yet been born. When scientists speak of your genome being unique, they are not engaging in flattery or reassurance, but stating a measurable biological reality. A study published by researchers at Decode Genetics in Iceland in 2017, examining the genomes of large family groups across multiple generations, found that each human being carries approximately 70 new mutations, 70 points at which your DNA sequence differs from both your mother and your father and your father. Not through inheritance, but through small copying errors or modifications that occurred when you were just a single cell dividing in the earliest moments of development. These de novo mutations, as geneticists call them, mean that your precise genetic sequence has never existed before in the history of life on Earth, and barring the creation of an exact clone, will never exist again after you are gone. You are, in the most literal biochemical sense, unprecedented. And yet, your genome, remarkable as it is, represents only the beginning of what makes you singular. From the moment of your birth, indeed, from the moment of your conception, your experience has been shaping the physical structure of your brain in ways that compound endlessly upon themselves. The synaptic connections between your neurons, the relative strengths and weaknesses of those connections, the particular patterns of activity that constitute your memories and habits and unconscious responses. These are formed and reformed continuously by every sensation you encounter, every thought you think, every moment of sleep during which your brain consolidates and reorganizes the experiences of the preceding day. Consider that there are 525,600 minutes in a single year. Each of those minutes represents countless neural events, synapses strengthening or weakening, connections forming or pruning away. The subtle architecture of your brain being sculpted by experience in real time. By the time you have lived 10 years, more than 5 million minutes have passed, each one contributing in its small way to the person you are becoming. By 30, by 50, by 70, the accumulated weight of these minutes has created a neural structure so particular to your specific history that no other brain in the universe could possibly replicate it. Not because such replication would be impossible in some fundamental physical sense, but simply because no other being could have experienced exactly what you have experienced, in exactly the order you experienced it, with exactly the emotional coloring and attentional focus that characterized each moment of your irreplaceable existence. The morning continues around you as these thoughts settle gently into the background, as the ordinary business of waking reasserts itself. Perhaps you swing your legs over the side of the bed. Perhaps you notice the particular quality of the light today, slightly overcast or perhaps unusually bright. And this noticing, this small act of perception, creates neural patterns that have never occurred in exactly this configuration before and will never occur in exactly this configuration again. The toast you eat for breakfast, if you eat toast, will be converted by your digestive system into simple molecules that will eventually find their way into new cellular structures, including, potentially, new neurons born in the hippocampus of your brain, where neurogenesis continues throughout adult life. In a universe as vast as the one we inhabit, a universe containing perhaps 2 trillion galaxies, each galaxy containing hundreds of billions of stars, many of those stars hosting planets, many of those planets perhaps hosting conditions suitable for the emergence of life. It seems almost inevitable that we should ask ourselves whether copies of everything might exist somewhere, whether the sheer scale of cosmic possibility might guarantee that somewhere, in some distant corner of space and time, there exists another being who is, in all essential respects, identical to you. This is not an unreasonable thought. It arises naturally from our intuitions about probability, from the basic mathematical principle that given enough chances, even extraordinarily unlikely outcomes must eventually occur. And yet, as we shall explore in the sections that follow, this intuition, comforting or troubling depending on your perspective, may not survive careful examination. The numbers involved in specifying a human being, the vast combinatorial space through which you emerged as the singular being you are, may be so much larger than even the most generous estimates of cosmic possibility that your uniqueness is not merely likely, but effectively guaranteed by the fundamental structure of mathematics itself. This is not a matter of faith or philosophy, but of calculation, of careful consideration of what the physical sciences tell us about the universe and what the biological sciences tell us about you. For now, though, let these facts rest lightly in your awareness. Let them settle like sediment in still water, requiring no immediate action or response. The morning does not demand that you grasp the full significance of your own improbability. The toast does not require you to contemplate the stellar origins of its carbon atoms. You may simply lie there, if you wish, in the gentle space between paragraphs, and allow the next thoughts to arrive when they are ready, in their own unhurried time, like clouds drifting across a quiet sky, like the slow revolution of the earth that brings each new dawn without effort or urgency. You are here, in this moment, in this body, and that is enough. That is, in fact, quite extraordinary, though it feels as ordinary as breath, as unremarkable as the morning light now brightening around you, as familiar as the sound of your own heart, which has been beating since before you were born, which will continue beating as you rest and listen, and perhaps, gradually, drift back toward the peaceful shores of sleep. The universe that surrounds you, the one you have been quietly existing within for all the years of your life, extends outward in every direction for distances that the human mind was never designed to comprehend. And yet, scientists have spent centuries carefully measuring it, cataloguing it, and attempting to describe its vastness in terms that might, with patience, begin to make sense to us here on this small planet, drifting through the dark, the observable universe, which is to say, the portion of all that exists from which light has had sufficient time to reach us since the beginning of everything, stretches approximately 93 billion light-years from one edge to the other, a figure that already seems impossible when you consider that a single light-year represents the distance that light itself travels in one complete year, moving at roughly 300,000 kilometers every second, never slowing, never tiring, simply streaming forward through the emptiness between stars. Within this observable sphere, this bubble of knowable space, centered wherever you happen to be standing or lying down at this particular moment, there exist approximately 2 trillion galaxies, a number that was revised significantly upward in 2016 when a team of astronomers led by Christopher Consalice at the University of Nottingham carefully re-examined the data we had accumulated over decades of peering outward and realized that our previous estimates had been far too conservative. 2 trillion galaxies means 2 million galaxies, each one containing somewhere between 100 million and several 100 billion stars, depending on its size and type, and around many of those stars there orbit planets of various compositions, some rocky like our own, some gaseous and vast, some frozen at the outer edges of their solar systems, and some perhaps temperate and blue with water, though we cannot yet see them clearly enough to know for certain. The sheer quantity of matter distributed throughout the observable universe is so large that astronomers have largely stopped trying to count individual objects and instead speak in terms of estimates and statistical averages, acknowledging that precision becomes meaningless when the numbers grow this incomprehensibly large. The story of how we came to understand that the universe extended so far beyond our own galaxy is itself a gentle one. unfolding over decades of patient observation and occasional moments of quiet revelation. And it begins in earnest with a man named Edwin Hubble, who in 1924 was working at the Mount Wilson Observatory in the mountains above Los Angeles, using what was then the largest telescope in the world. A great reflecting instrument with a mirror 2.5 meters across. At the time, there was considerable debate among astronomers about whether the faint smudges of light visible in the night sky, which they called spiral nebulae, were small clouds of gas within our own Milky Way galaxy, or whether they might be something far more extraordinary, entire galaxies unto themselves, separated from us by distances too great to easily imagine. Hubble spent many long nights photographing one particular nebula in the constellation Andromeda, searching for individual stars within its hazy glow. And eventually he found what he was looking for, a type of star called a Cepheid variable, which brightens and dims in a regular pattern that allows astronomers to calculate its true luminosity and therefore its distance. When Hubble completed his calculations, the result was startling in its quiet way. For the Cepheid he had found was not thousands of light years away, as it would need to be if Andromeda were merely a cloud within the Milky Way, but rather something like 900,000 light-years distant, placing it far outside the boundaries of our galaxy entirely. The number has since been revised upward to approximately 2.5 million light-years as our measurements have improved. But the essential discovery remained unchanged. For Hubble had proven that the universe contained not merely one galaxy, but many, perhaps countless, each separated from the others by vast gulfs of empty space. This understanding of the universe as containing billions upon billions of galaxies was already humbling enough. But it was only the beginning, for throughout the 20th century, astronomers continued to push their observations further and to develop new instruments capable of seeing ever more distant and ancient light. One of the most remarkable of these efforts occurred in December of 1995, when the Hubble Space Telescope, named in honor of the same Edwin Hubble who had revealed the existence of external galaxies 7 decades earlier, was turned toward a small and apparently empty patch of sky in the constellation Ursa Major, near the handle of what is sometimes called the Big Dipper. The decision to do this was made by Robert Williams, who was then the director of the Space Telescope Science Institute, and it was considered by many of his colleagues to be a considerable risk, for the telescope's observing time was precious and highly sought after, and pointing it at nothing, at a tiny dark square of sky where no interesting objects were known to exist, seemed to some an extravagant waste. Williams, however, had a hunch that even the emptiest seeming portions of the sky might reveal something worthwhile if only we looked long enough and carefully enough. And so the telescope was held steady on that one small patch, about 1/24 millionth of the total sky, for 10 consecutive days, gathering every faint photon that reached its mirror from the depths of space. When the resulting image was assembled and released to the public, it became one of the most important photographs ever taken, not because of any single dramatic discovery, but because of what it revealed about the sheer abundance of the universe. In that tiny patch of darkness, that speck of sky so small you could cover it with a grain of sand held at arm's length, there appeared not emptiness, but thousands upon thousands of galaxies, each one a vast collection of stars, each one separated from its neighbors by millions of light years. Each one home to processes and structures we could barely begin to understand. The Hubble Deep Field, as the image came to be known, demonstrated that wherever we chose to look, however unpromising the view might seem, the universe was filled with structure and complexity extending back to the earliest epochs of cosmic time. Some of the galaxies in the image were so distant that their light had been traveling toward us for more than 12 billion years, meaning we were seeing them not as they are now, but as they were when the universe itself was young, still assembling its first generations of stars. All of this might suggest that the observable universe, vast as it is, represents the totality of what exists. But there is good reason to believe that it does not, that the space beyond the horizon of our observations continues onward, perhaps without end, and that what we can see is merely a small fraction of a much larger, possibly infinite expanse. The idea that the universe might extend far beyond what we can observe arises from a theory called cosmic inflation, which was first developed in its modern form by a physicist named Alan Guth in 1979. During a period when he was working as a postdoctoral researcher at Stanford University and feeling somewhat uncertain about the direction of his career, Guth had become interested in some puzzling features of the standard cosmological model of the time, particularly the question of why the universe appeared so uniform in all directions. Why distant regions of space that had never been in contact with one another, nevertheless, seemed to have nearly identical properties, as though they had somehow agreed in advance on the temperature and density they would adopt. The conventional Big Bang theory had no satisfying explanation for this uniformity, and Guth spent many months contemplating the problem, filling notebooks with calculations and discarded ideas. The solution came to him late one evening in December of 1979, in his small office on the Stanford campus, when he realized that if the universe had undergone a brief but extraordinarily rapid period of expansion in its earliest moments, a period during which space itself stretched outward far faster than the speed of light, then many of the puzzles that had troubled cosmologists could be elegantly resolved. This inflationary epoch, lasting only a tiny fraction of a second, would have taken a region of space smaller than an atom and expanded it to a size vastly larger than the observable universe of today, smoothing out any irregularities and ensuring that distant parts of space would share the same properties simply because they had all originated from the same minuscule patch. Guth recognized the significance of what he had found, and in his notebook that night, he drew a box around the words "spectacular realization." Though the discovery itself was quiet, a moment of private clarity in an empty office late at night, the kind of unwitnessed breakthrough that occurs more often than dramatic retellings might suggest. The implications of inflation for the size of the universe are profound and somewhat unsettling. For if the theory is correct, then the space beyond our observable horizon is not merely a little larger than what we can see, but unimaginably, perhaps infinitely, larger. The region that underwent inflation was so vast, and the expansion was so extreme, that we have no way of knowing where its edges might be, or indeed whether it has edges at all. Some versions of inflationary theory suggest that the process never truly stops, that somewhere beyond the limits of our observation, space is still inflating, still stretching outward, creating new regions of universe faster than we could ever hope to explore them. This idea, sometimes called eternal inflation, paints a picture of a cosmos that is not a single bubble of space, but an endless froth of bubbles. Each one a universe unto itself, each one potentially governed by different physical constants and different arrangements of matter. One way that cosmologists have attempted to determine whether the universe is finite or infinite is by measuring its geometry, the shape of space itself on the largest scales, in a universe that curves back on itself, like the surface of a sphere extended into higher dimensions. Space would be finite, and if you traveled far enough in any direction, you would eventually return to where you started, though the journey would take longer than the current age of the universe permits. In a universe that curves the opposite way, like a saddle, space would also have particular geometric properties that could be detected through careful measurement. But if space is perfectly flat, neither curving inward nor outward, then it could in principle extend forever in all directions, without boundary or edge, simply going on and on in an endless expanse of galaxies and stars and darkness. The Planck satellite, a European Space Agency mission that operated from 2009 to 2013 and released its final results over the following years, was designed in part to measure this curvature with extraordinary precision by studying the faint afterglow of the Big Bang, known as the cosmic microwave background radiation. This radiation, which fills all of space and reaches us from every direction, carries within its subtle patterns information about the geometry and composition of the universe. And by analyzing it carefully, scientists can determine how flat or curved space truly is. The results of the Planck mission, published in a series of papers between 2013 and 2018, indicated that the universe is geometrically flat to within the limits of what the instruments could measure, with any curvature being so slight as to be indistinguishable from zero. This finding is consistent with, though it does not prove, the idea that the universe is infinite, that space continues outward without limit, containing more galaxies, more stars, more planets than any census could ever count. And here, at last, we arrive at the quiet question that underlies this entire exploration. The question that seems almost inevitable once you accept that the universe might be infinite. If space goes on forever, and if matter is distributed throughout that space in accordance with the same physical laws that govern our own corner of the cosmos, then it would seem to follow that every possible arrangement of atoms that is not forbidden by those laws must occur somewhere, given enough space in which to occur. An infinite universe would contain not merely a very large number of variations, but every variation, repeated an infinite number of times, including arrangements of atoms that precisely duplicate the arrangement that constitutes you at this very moment. Every cell, every neuron, every fleeting thought, replicated exactly in some unimaginably distant region of space. This reasoning has led some cosmologists to suggest that in an infinite universe, you are not unique, that there exist countless copies of you, living lives identical to yours in every detail, distributed throughout the endless expanse at intervals too large to comprehend, but nevertheless real, nevertheless present, nevertheless existing in exactly the same way that you exist here and now. It is a strange idea, and whether it is true depends on assumptions that remain uncertain. And in the sections that follow, we will examine those assumptions with care and patience, allowing the mathematics and the physics to guide us toward a more complete understanding. One gentle step at a time. Let us begin with what seems, at first, to be a rather simple argument, the kind of reasoning that feels almost impossible to refute once you have followed its logic from beginning to end. It is an argument about arrangements, about the finite number of ways that things can be organized within any given region of space, and about what happens when you have an infinite amount of space in which those arrangements might occur. This is the mathematical case for your duplicates, for the idea that somewhere out there, impossibly far away, but nonetheless real, there exists another version of you, identical in every meaningful sense, living out a life that mirrors your own down to the last remembered dream and the last forgotten afternoon. The argument is elegant, it is straightforward, and it has convinced a great many careful thinkers over the years that such copies must, by mathematical necessity, exist. The reasoning proceeds something like this. Imagine that you have a box, a region of space with definite boundaries, and imagine that within this box there are particles, atoms, the basic constituents of matter arranged in various configurations. Now, the laws of physics tell us that there is a smallest meaningful unit of space, a scale below which our current understanding of physics becomes uncertain, and similarly, there is a smallest meaningful unit of energy, a granularity to the way that particles can be arranged and can move. This means that within any finite box, there is not an infinite number of possible arrangements of matter and energy, but rather a very large yet ultimately finite number of possible states. The box can only be configured in so many distinct ways, even if that number is astronomically, incomprehensibly large. The physicist Max Tegmark, in a 2003 article published in Scientific American, worked through this calculation with characteristic clarity, asking a question that seems almost whimsical until you realize how seriously the mathematics takes it. He asked how far away your nearest identical copy might be. If the universe is indeed infinite in spatial extent, and if matter is distributed more or less evenly throughout that infinity. His reasoning was straightforward. If there are only finitely many ways to arrange the particles within a region of space the size of the observable universe, and if the infinite universe contains infinitely many such regions, then by simple logic, arrangements must repeat. They must repeat infinitely often, in fact, and therefore, somewhere out there, at some calculable distance, there must be a region arranged in exactly the same way as the region you currently occupy, complete with an identical version of you reading or listening to these very words. The number Tegmark arrived at was 10 to the power of 10 to the power of 29 meters. A distance so vast that it defeats ordinary comprehension entirely. A number so large that writing it out in full would require more digits than there are atoms in the observable universe. And yet, in an infinite universe, such distances are meaningless in a certain sense, because infinity contains all distances, no matter how large, infinitely many times over. The argument suggests that not only does one copy of you exist at that impossible remove, but infinitely many copies, scattered throughout the endless reaches of space, each one convinced of their own uniqueness, each one perhaps lying in bed at this very moment, listening to these same gently spoken words. To understand where this line of thinking originates, we must travel back in time to 19th century Vienna, to the work of a physicist named Ludwig Boltzmann, who spent much of his career wrestling with questions about heat, randomness, and the behavior of gases. Boltzmann was one of the founders of statistical mechanics, the branch of physics that explains how the large-scale properties of matter, things like temperature and pressure, emerge from the chaotic motions of countless individual atoms and molecules. He showed that entropy, the measure of disorder in a physical system, tends to increase over time, not because of any fundamental law forbidding its decrease, but simply because disordered states are vastly more numerous than ordered ones, and so random processes will almost always move a system from order toward disorder rather than the reverse. But Boltzmann understood something troubling about this reasoning, something that has haunted physics ever since. If the universe is infinite in extent and eternal in duration, if random fluctuations are constantly occurring throughout its vast reaches, then given enough time and enough space, those fluctuations should occasionally produce, entirely by chance, configurations of matter that are highly ordered, configurations that are enormously improbable but not impossible. In particular, Boltzmann realized, random fluctuations should occasionally produce conscious observers, brains capable of thought and perception, assembled entirely by accident from the random jostling of particles in the void. This idea was given a name much later, in 2004, when the physicists Andreas Albrecht and Lorenzo Sorbo formally christened these hypothetical beings as Boltzmann brains, random fluctuations in the quantum fields, or the thermal bath of particles that momentarily coalesce into something capable of conscious experience before dissolving back into chaos. The concept is deeply unsettling when you think about it carefully, because if such brains are possible at all, and the laws of physics seem to suggest they are, then in an infinite universe there should be vastly more Boltzmann brains flickering briefly into existence than there are ordinary observers like us, who came into being through the long, slow process of cosmic evolution, star formation, planetary accretion, and biological development. But let us set aside the Boltzmann brain problem for now, though it will become important later in our story, and return to the basic argument for your duplicates. The argument depends crucially on the assumption that space is infinite, or at least very much larger than what we can see, and it depends on the assumption that matter is distributed through that space in a roughly uniform way. The same kinds of particles with the same kinds of properties existing everywhere, not just in our local neighborhood. These are assumptions that many cosmologists take seriously, based on our observations of the cosmic microwave background radiation, the ancient light that has been traveling toward us for nearly the entire history of the universe. When we look out into space, we are looking back in time, because light travels at a finite speed, and so the more distant an object is, the longer its light has taken to reach us. There is a limit to how far we can see, a boundary called the particle horizon, which is determined by the age of the universe and the speed of light. Light has been traveling for approximately 13.8 billion years since the universe became transparent enough for photons to stream freely through space. And so the particle horizon lies at a distance of about 46 billion light-years in every direction. The discrepancy between this number and the age of the universe being due to the expansion of space itself during that time. Beyond this horizon, there may be more universe, perhaps infinitely more, but we cannot see it and we cannot receive any signals from it. Not yet, not ever. If the universe continues to expand, as it is currently doing. Within the observable universe, the region bounded by our particle horizon, there are approximately 10 to the power of 80 atoms, a number that is itself almost impossible to visualize. Roughly a 1 followed by 80 zeros. This is a very large number, but it is decidedly finite, and it places an upper limit on the number of distinct ways that matter can be arranged within any region the size of our observable universe. If you calculate the number of possible quantum states for this many particles, you get a number that is large beyond ordinary comprehension, but still finite, something like 10 to the power of 10 to the power of 118, or thereabouts, depending on exactly how you count. And this is where the argument for duplicates takes hold. If there are only finitely many ways to arrange a region of space, and if there are infinitely many such regions in an infinite universe, then every possible arrangement must be realized somewhere, and in fact must be realized infinitely many times. The specific arrangement that constitutes you, your body, your brain, your immediate surroundings, all the particles in all their precise positions and momenta, must occur again and again and again, scattered throughout the infinite reaches of space, each copy separated from the others by those unimaginable distances that Tegmark calculated. The cosmologist Alexander Vilenkin, working at Tufts University, has spent much of his career developing the theory of eternal inflation, a framework that suggests our observable universe is just one bubble in a vast, perhaps infinite, foam of pocket universes, each one born from a moment of cosmic inflation, and each one potentially giving rise to new universes in turn. In Vilenkin's picture, the inflationary process never truly ends, at least not everywhere at once. And so the production of new pocket universes continues eternally, generating an infinite ensemble of cosmic regions in which every possible initial condition is realized, every possible history played out, every possible version of every possible observer living out every possible life. If this picture is correct, then the argument for your duplicates becomes even stronger. Because now we have not just one infinite space, but infinitely many infinite spaces. An infinity of infinities. A structure so vast that the mind recoils from contemplating it directly. And in such a structure, the reasoning goes, the existence of your exact duplicates is not merely possible, but absolutely certain. Guaranteed by the mathematics of infinity and finite possibility. This line of reasoning has convinced many physicists that we must take the idea of infinite copies seriously, that somewhere out there, no matter how far, there are other versions of you, other versions of everyone you have ever known, other versions of every moment you have ever experienced. The logic seems airtight, the mathematics unimpeachable. If space is infinite and possibilities are finite, then repetition is inevitable. This is the argument in its purest form, elegant and unsettling, and apparently inescapable. And yet, as we rest here in the gentle quiet of this reasoning. As we let the numbers wash over us without demanding that we hold them all in mind at once, it is worth pausing to notice that something subtle has happened in the course of this argument. We have taken concepts that make perfect sense in ordinary finite contexts, concepts like arrangement and repetition and identity, and we have extended them into the infinite, trusting that they will continue to behave in familiar ways. We have assumed that infinity is simply a larger version of the finite, that what is true of large numbers remains true when those numbers grow without bound. But what if the mathematics is hiding something deeper? What if the assumptions buried in this elegant argument are not quite as innocent as they appear? What if infinity is stranger and more subtle than the simple extrapolation of finite reasoning would suggest? This is the question we will turn to shortly, not to reject the mathematics, but to look more carefully at its foundations, to ask what it really means to speak of repetition in an infinite universe, and whether the concept of your duplicate makes as much sense as it first appears to. For now, though, let the argument rest in your mind, neither accepted nor rejected, simply present, a possibility to be explored further as we continue together through this quiet consideration of what it means to be, in all the vastness of space and time, the particular arrangement of matter and memory that is uniquely and unrepeatable you. Let us turn now to something rather fundamental, something woven into the very fabric of reality itself, and that is the curious behavior of matter and energy at scales so small that our ordinary intuitions cease to apply. This is the domain of quantum mechanics, a field of physics that emerged in the early 20th century and revealed, somewhat unexpectedly, that the universe operates according to rules quite different from those we experience in our everyday lives. And within this domain lies perhaps the most profound reason why you, as you exist in this precise moment, could never be duplicated, not even across the vast expanses of an infinite cosmos. The story begins, as many stories in physics do, with a difficulty. By the 1920s, physicists had accumulated a substantial body of experimental evidence that simply could not be explained by the classical theories of Newton and Maxwell. Light behaved sometimes as a wave and sometimes as a particle. Atoms, those supposedly indivisible building blocks, were found to contain electrons that orbited in peculiar patterns, occupying only certain energy levels and never anything in between. Something new was needed, some fresh framework that could account for these strange observations. And it arrived through the collective work of many brilliant minds, though we shall focus here on a particular contribution made in 1927. In that year, a young German physicist named Werner Heisenberg, working in Copenhagen alongside Niels Bohr, formulated what has come to be known as the uncertainty principle. This principle states, in essence, that there exist fundamental limits to what we can know about a particle at any given moment. If we measure the position of an electron with great precision, we necessarily introduce uncertainty into our knowledge of its momentum, and vice versa. This is not a limitation of our instruments or our cleverness. It is, rather, a fundamental feature of reality itself. The universe, at its most basic level, does not permit the simultaneous exact knowledge of certain pairs of properties. Heisenberg expressed this mathematically. showing that the product of the uncertainties in position and momentum must always exceed a certain minimum value, a value related to Planck's constant, that tiny number that governs the quantum realm. Now, one might be tempted to think that this uncertainty is merely a reflection of our ignorance, that the particles themselves have definite positions and momenta, and we simply lack the means to measure them without disturbance. This interpretation, sometimes called the hidden variables hypothesis, suggests that the apparent randomness of quantum mechanics conceals an underlying determinism, much as the shuffling of a deck of cards appears random, but is, in principle, fully determined by the initial positions and movements of the cards. This is a comforting thought, perhaps, for those who prefer a clockwork universe. But it is almost certainly wrong. To understand why, let us consider an experiment first performed in 1801 by Thomas Young, an English polymath who made contributions to fields as varied as linguistics and medicine. Young directed a beam of light through two narrow slits cut in an opaque barrier and observed the pattern that appeared on a screen beyond. What he saw was not two bright bands corresponding to the two slits, as one might expect if light consisted of simple particles traveling in straight lines. Instead, he observed a series of alternating bright and dark bands, a pattern characteristic of wave interference, where the crests of waves from the two slits arrived together. They reinforced each other, producing brightness. Where a crest met a trough, they cancelled, producing darkness. This was strong evidence that light is a wave. But the story does not end there. More than a century later, in 1927, Clinton Davison and Lester Germer, working at Bell Telephone Laboratories in the United States, performed an experiment that would reveal something even more surprising. They directed a beam of electrons at a crystalline nickel surface and observed the pattern of electrons that scattered from it. Electrons, which were known to be particles, possessing mass and charge, produced a diffraction pattern entirely consistent with wave behavior. The electrons, it seemed, were interfering with themselves, and when similar experiments were performed with the electrons passing through two slits, one at a time, the interference pattern still appeared, built up gradually from the accumulated arrivals of individual electrons. Each electron, somehow, passed through both slits simultaneously, interfering with itself before arriving at a particular point on the detector. This is profoundly strange behavior, and it resists any classical explanation. But what makes it relevant to our present discussion is what happens when we try to determine which slit each electron actually passes through. If we place detectors at the slits to observe the electron's path, the interference pattern vanishes. The very act of measurement collapses the wave-like behavior, and the electrons begin to behave as ordinary particles, passing through one slit or the other, but not both. It is as though the universe permits the electron to exist in a state of quantum superposition, a combination of passing through both slits, but only so long as we do not inquire too closely into its business. Now, one might still hope that some deeper theory could explain these results without invoking genuine randomness. Perhaps the electrons do have definite paths, guided by hidden variables we cannot access. This possibility was addressed, with remarkable clarity, by the physicist John Stuart Bell in 1964. Bell, working then at CERN in Geneva, derived a mathematical inequality, now known as Bell's inequality, that any theory relying on hidden variables and local causation must satisfy. If the universe operates according to such a theory, then certain correlations between measurements on distant particles must remain below a particular threshold. Quantum mechanics, however, predicts correlations that exceed this threshold. The two theories make different predictions, and experiments can decide between them. The crucial experiments were performed in 1982 in Paris by a physicist named Alain Aspect and his colleagues. They created pairs of photons in a state of quantum entanglement, a condition in which the properties of the two particles are correlated in ways that cannot be explained by any shared information carried from their common origin. The photons were sent to distant detectors, and their polarizations were measured. The results agreed precisely with the predictions of quantum mechanics and violated Bell's inequality by a wide margin. The hidden variables interpretation, at least in its simplest form, was ruled out. The correlations between the distant photons were real, and they could not be explained by any pre-existing information encoded in the particles themselves. This work, along with complementary experiments by John Clauser in California during the 1970s and later refinements by Anton Zeilinger and his group in Vienna, established beyond reasonable doubt that quantum mechanics involves genuine, irreducible randomness. In 2010, Zeilinger's team conducted experiments specifically designed to test whether the outcomes of quantum measurements could be predicted by any mechanism whatsoever, and they found that the randomness was as complete as the theory suggested. There is no deeper layer of reality that determines which way a quantum coin will land. The outcome is created in the moment of measurement, not revealed from some pre-existing fact. This brings us to the year 2022, when the Nobel Prize in Physics was awarded jointly to Aspect, Clauser, and Zeilinger for their decades of work on quantum entanglement and the experimental violation of Bell's inequalities. The committee recognized not only the profound implications of their work for our understanding of reality, but also the practical applications that have emerged, including quantum cryptography and the early development of quantum computing. But, for our purposes, the recognition served as a confirmation of what physicists had long suspected. The universe is not deterministic in the classical sense, and the randomness we observe at the quantum level is fundamental. Let us now consider what this means for you, personally. Your body is composed of atoms, roughly 7 octillion of them, and each of these atoms has a quantum history. Consider the atoms of carbon in your bones and muscles and brain. Many of these carbon atoms were forged in the cores of ancient stars, produced through nuclear fusion reactions that occurred billions of years ago. But a small fraction of the carbon in your body is carbon-14, a radioactive isotope created when cosmic rays strike nitrogen atoms in the upper atmosphere. Carbon-14 decays over time, transforming into nitrogen-14 through a process called beta decay, in which a neutron emits an electron and becomes a proton. The half-life of carbon-14 is approximately 5,730 years, meaning that in any given sample, About half of the carbon-14 atoms will decay within that span of time. But the crucial point is this: there is no way to predict exactly when any particular carbon-14 atom will decay. We can calculate probabilities with exquisite precision, but the exact moment of decay is fundamentally undetermined. It is a quantum event, subject to the irreducible randomness that Heisenberg's uncertainty principle implies. The particular atoms of carbon-14 that decayed in your body yesterday, and the ones that will decay tomorrow, follow a pattern that could never be replicated, not even in principle. The same is true of every photon that has ever been absorbed by the molecules in your eyes, every electron that has ever jumped between energy levels in the cells of your skin, every quantum fluctuation in the neurons of your brain. When a neuron fires, it does so because of a cascade of electrochemical events that ultimately depend on quantum processes, the opening and closing of ion channels, the binding of neurotransmitter molecules to receptors, the movement of charged particles across membranes. Each of these processes involves probabilities, and the precise sequence of events that constitutes your thoughts, your memories, your very consciousness, is shaped by quantum randomness at every moment. Consider, now, the moment of your conception. A single sperm cell, out of the hundreds of millions released, fused with an egg, combining genetic material from your parents into a new and unique genome. But which sperm cell reached the egg first was not a matter of pure mechanical necessity. The motion of sperm cells is influenced by countless factors, including the random thermal motion of the molecules around them, the precise concentration of chemical gradients, and the subtle quantum events within their cellular machinery. The outcome, your existence, hinged on events that were not predetermined, that could have gone differently in ways that no amount of prior information could have predicted. Even if we were to imagine constructing a perfect replica of the conditions present at the moment of your conception, down to the position and momentum of every particle involved, we would find that quantum uncertainty forbids such precision. We cannot, even in principle, specify the initial conditions with sufficient accuracy to guarantee the same outcome. The universe would produce a different result, a different combination of genetic material, a different person. You, as you are, emerged from a particular confluence of quantum events that will never recur. And this is true not only for the moment of your conception, but for every moment of your existence since. Every breath you have taken has involved the random collision of trillions of molecules with the surfaces of your lungs. Every meal you have eaten has been digested through chemical reactions governed by quantum mechanics. Every memory you have formed has been encoded through processes that, at their deepest level, involve the same irreducible randomness that Bell and Aspect and Zeilinger have demonstrated. There is a certain comfort, perhaps, in recognizing that your existence is not merely improbable, but genuinely unrepeatable. You are not one of many possible copies scattered across an infinite cosmos. You are the only version of yourself that will ever exist, the unique product of a particular sequence of quantum events that unfolded exactly once and will never unfold again. The atoms that compose your body carry within them a history that is yours alone, a record of quantum randomness that cannot be duplicated. And so, as you rest here now, breathing slowly and allowing your thoughts to settle. You might consider that the very particles of your being are participating in a story that began with the first stars and continues through this present moment, shaped at every turn by the gentle, unpredictable unfolding of quantum events. There is nothing hurried about this process. It proceeds at its own pace, creating as it goes, weaving together the threads of chance into the singular tapestry of your existence. There is a quality to time that we often take for granted, a peculiar, one-directional nature that seems so obvious we rarely pause to consider why it should be so. And yet, when you examine it closely, when you sit with the question of why time moves forward and never back, you find yourself drawn into one of the most profound mysteries of physics, a mystery that touches directly upon why you, in your particular form, with your particular history and memories and cellular architecture, could never be replicated or rewound, could never emerge again in quite the same way. Even if the universe were to continue for an eternity of eternities, stretching outward into incomprehensible spans of duration, to understand this peculiar directionality of time, we must travel back to 19th century Germany, to a period of remarkable intellectual ferment, when natural philosophers were beginning to unravel the fundamental laws governing heat and energy and work. And it was here, in 1865, that a German physicist named Rudolf Clausius introduced a concept that would forever change our understanding of the physical world, a concept he called entropy, deriving the word from the Greek entropia, meaning transformation. And with this single term, Clausius gave us the vocabulary to describe something that had long been intuitively felt but never precisely articulated. Namely, that there exists in nature a fundamental tendency toward disorder, a gentle but inexorable drift from the organized to the disorganized, from the concentrated to the dispersed, from the improbable to the probable. Clausius observed that heat naturally flows from warmer bodies to cooler ones, never the reverse, and that whenever energy is transformed from one form to another, some portion of it becomes unavailable for useful work, dispersing into the surrounding environment in ways that cannot be easily recovered. And this insight, seemingly simple, contained within it a profound truth about the nature of physical processes, namely, that there exists a directionality to change, a preferred orientation in which the universe unfolds. And this directionality, Clausius recognized, could be quantified through his concept of entropy, which he showed must always increase or remain the same in any isolated system, never decreasing, never running backward, always accumulating like sand settling slowly to the bottom of a still pond. Some 60 years later, in 1927, the British astrophysicist Arthur Eddington delivered a series of lectures at the University of Edinburgh, the prestigious Gifford Lectures, which would later be published under the title The Nature of the Physical World. And it was in these lectures that Eddington gave us another phrase that has since become central to our understanding of time and thermodynamics, a phrase both poetic and precise, which he called the arrow of time. And with this metaphor, Eddington captured something essential about our experience of temporal flow, the sense that time moves in one direction like an arrow in flight, never circling back, never reversing its course, always pointing from past to future, from before to after, from memory to anticipation. Eddington understood that this arrow of time is intimately connected to the second law of thermodynamics, to Clausius's principle of ever-increasing entropy, for it is precisely this tendency toward greater disorder that distinguishes the past from the future, that allows us to recognize the direction in which events unfold. And he noted that while the fundamental equations of physics appear to work equally well whether time runs forward or backward, the statistical behavior of large numbers of particles reveals a clear preference for one direction over the other, and this preference, subtle but absolute, number 10, is what gives our universe its temporal character, its quality of irreversible becoming rather than reversible being. But if we are to fully appreciate the thermodynamic arrow of time, we must consider not just abstract principles, but the actual physical history of our universe. And for this, we turn to a remarkable discovery made in 1965 at Bell Telephone Laboratories in New Jersey, where two radio astronomers named Arno Penzias and Robert Wilson were working with a sensitive horn antenna originally designed for satellite communication. And as they calibrated their instrument, they found themselves troubled by a persistent background noise, a faint hiss that seemed to come from every direction in the sky equally, that could not be attributed to any known source or eliminated by any adjustment to their equipment. And after exhausting all other possibilities, including the removal of pigeon droppings from inside the antenna, they realized that they had inadvertently detected something extraordinary: the cosmic microwave background radiation, a faint glow of electromagnetic energy that permeates the entire observable universe. This radiation, Penzias and Wilson came to understand with the help of theoretical physicists at nearby Princeton University, was nothing less than the afterglow of the Big Bang itself, the remnant heat of that primordial explosion stretched and cooled by the expansion of space over billions of years. And when cosmologists studied this radiation in greater detail, particularly through later satellite missions that mapped its subtle variations across the sky, they found something of profound significance for our understanding of entropy and time, namely that the early universe was in a state of remarkably low entropy, of extraordinary uniformity and smoothness, a highly ordered initial condition from which all subsequent complexity has emerged. And it is this low entropy beginning that explains why the arrow of time points in the direction it does. For given such an improbable starting point, the only possible direction of change is toward greater disorder, toward higher entropy, towards the statistical equilibrium that the universe is slowly and inexorably approaching. Consider now how this thermodynamic arrow of time has expressed itself in your own existence, in the particular trajectory that brought you from a single fertilized cell to the incomprehensibly complex organism you are today. For this developmental journey, though it may seem to have produced greater order rather than greater disorder, is in fact a beautiful illustration of how ordered structures can arise within the general flow toward entropy, how local decreases in disorder can occur at the expense of larger increases elsewhere. And understanding this apparent paradox will bring us closer to appreciating why your particular developmental path could never be repeated. When a sperm cell and egg cell unite, they form a single diploid cell called a zygote, containing a complete set of genetic instructions encoded in the particular arrangement of nucleotides along your chromosomes. And this single cell, then begins a process of division and differentiation that will eventually produce an adult human body comprising approximately 37 trillion cells. An almost incomprehensible number. And each of these cells occupies a specific location, performs a specific function, expresses a specific subset of your genetic instructions, and connects to other cells in patterns of exquisite specificity. And the question naturally arises, how can such elaborate organization emerge if the universe tends always toward greater disorder? The answer lies in the fact that biological development is not a closed system, but an open one, constantly exchanging matter and energy with its environment. And as the developing embryo constructs its ordered structures, it does so by dissipating energy, by consuming nutrients and releasing heat, by increasing the entropy of its surroundings far more than it decreases its own internal entropy. And the net effect, when you account for all the energy transformations involved, is always an increase in the total entropy of the universe, in perfect accordance with the second law. And this understanding was significantly deepened by the work of the Belgian physical chemist Ilya Prigogine, who in 1977 received the Nobel Prize in Chemistry for his contributions to non-equilibrium thermodynamics, particularly his theory of dissipative structures. Prigogine showed that far from equilibrium, in systems through which energy continuously flows, there can arise spontaneously organized patterns and structures that maintain themselves by dissipating energy, structures that exist not despite the second law of thermodynamics, but because of it. And he called these dissipative structures, recognizing that their order is maintained through ongoing dissipation, through continuous entropy production, and living organisms, Prigogine understood, are perhaps the most remarkable examples of dissipative structures in the known universe, maintaining their internal organization over extended periods of time by constantly processing energy and matter, by eating and breathing and metabolizing, by swimming against the current of entropy through ceaseless thermodynamic effort. Your development from zygote to embryo to fetus to infant to child to adult followed a path that was shaped by countless thermodynamic processes, each of which left an irreversible mark on the universe, each of which increased the total entropy of the cosmos in a pattern that can never be exactly undone. And the particular sequence of cell divisions, the precise timing of gene expression, the exact concentrations of signaling molecules at each moment of development, the specific ways in which your neurons extended their axons and formed their connections, all of these processes were influenced by thermal fluctuations, by the random jostling of molecules, by chance events at the molecular level that bias the outcome in one direction rather than another. And because these thermal fluctuations are inherently unpredictable, governed by the probabilistic laws of statistical mechanics, your developmental trajectory was not deterministically specified by your genes alone, but emerged from the interaction of genetic instructions with an ocean of molecular noise, each ripple of which pushed your development along a particular path among countless possible paths. This brings us to the question of memory, of how your experiences are recorded in the physical structure of your brain. And here we encounter yet another profound illustration of thermodynamic irreversibility. For your memories are not like words written on a page that could be erased and written again. but are instead encoded in the specific strengths and configurations of synaptic connections between your neurons, in patterns that were shaped by particular sequences of neural activity that can never recur in exactly the same way. And our understanding of these processes was significantly advanced by the work of the Austrian-American neuroscientist Erich Kandel, who in the year 2000 received the Nobel Prize in Physiology or Medicine for his discoveries concerning signal transduction in the nervous system and the molecular mechanisms underlying memory formation. Kandel and his colleagues, working initially with the sea slug Aplysia and later with mice and other organisms, showed that memories are formed through physical changes in the connections between neurons, through alterations in the strength and number of synapses, through the growth of new dendritic spines and the pruning of old ones. And these changes occur through specific biochemical pathways involving gene expression and protein synthesis. Processes that are themselves thermodynamically irreversible, that leave lasting traces in the physical structure of neural tissue. And once these traces are formed, they cannot simply be undone by running time backward, any more than a broken egg can spontaneously reassemble itself, or a cup of tea can spontaneously separate back into hot water and disperse tea molecules. Your memories, then, are physical inscriptions in the matter of your brain, patterns of synaptic connectivity that were laid down through irreversible thermodynamic processes, shaped by the specific sequence of experiences you happen to encounter, by the particular sensory inputs that activated particular neural pathways at particular moments in your particular life. And because each memory formation event increased the entropy of the universe in a slightly different way, because each moment of your experience was accompanied by a unique pattern of metabolic heat dissipation and molecular rearrangement, the configuration of memories encoded in your brain represents a thermodynamic history that can never be repeated. A record of entropy production that is as unique as a fingerprint and far more complex. Each heartbeat that has ever occurred in your chest released heat into your surroundings. Each breath dispersed carbon dioxide into the atmosphere. Each thought required the consumption of glucose and the production of metabolic byproducts. And the cumulative effect of all these processes, extended over the years and decades of your existence, has been to increase the entropy of the universe in a pattern so intricate, so dependent on the precise sequence of events that constituted your life, that no other being, in no other time or place, could ever replicate it exactly. And this thermodynamic history is as much a part of your identity as your name or your face, a wake of entropy trailing behind you through time, like the wake of a ship through water, marking your passage through the universe in a signature that can never be forged, never be counterfeited, never be produced again by any natural process or any conceivable technology. In the year 1927, a Belgian priest and physicist named Georges Lemaitre was working quietly with the equations of general relativity, and what he found in those calculations would eventually change the way we understand our place in the cosmos. Though at the time his work received little attention from the wider scientific community, Lemaitre discovered, through careful mathematical reasoning, that the universe itself could not be static, that the fabric of space was not fixed in place like a great unchanging stage upon which the drama of existence unfolds, but rather that space itself was stretching, pulling apart, carrying the galaxies along with it like raisins in a loaf of bread that rises slowly in a warm oven. This was a strange and unsettling idea, and even Albert Einstein, whose own equations had hinted at this possibility, initially dismissed Lemaitre's conclusions, telling him that while his mathematics was correct, his physics was abominable. But the universe, as it so often does, paid no attention to what anyone preferred to believe, and within just a few years, observational evidence from Edwin Hubble would confirm that distant galaxies were indeed receding from us in every direction. Their light stretched toward the red end of the spectrum in direct proportion to their distance. This expansion of space has profound implications for the question of whether you might encounter another version of yourself somewhere in the vastness of existence, because it means that the cosmos is not a simple container with fixed boundaries through which light might eventually travel from any point to any other point given sufficient time. Instead, space is growing, and it is growing everywhere, not from a single central point, but uniformly throughout the entire fabric of reality, so that the distance between any two sufficiently separated objects increases with every passing moment, even if neither object is moving through space in any ordinary sense. You might picture this by imagining two ants standing still on the surface of a balloon that is being slowly inflated, each ant perfectly motionless on the rubber surface, yet the distance between them increasing steadily as the balloon expands beneath their feet. This is not a perfect analogy, because the universe is not a two-dimensional surface, and space does not require anything outside of itself into which it expands, but it captures something essential about the nature of cosmic expansion, which is that the very medium through which light must travel is itself growing larger, and this growth has consequences for what we can ever hope to see or know. The consequences become particularly interesting and particularly relevant to our present discussion when we consider the cosmological horizon, which is the boundary beyond which we cannot receive any information at all. Not because there is nothing there, but because the expansion of space carries that region away from us faster than light can travel toward us. This is not a violation of the principle that nothing can move through space faster than light, because the galaxies beyond our horizon are not moving through space at superluminal velocities. They are simply being carried away by the expansion of space itself, and there is no law of physics that prevents space from stretching at any rate whatsoever. The light from those distant regions is indeed traveling toward us at the constant speed of light relative to its local space. But the space between us and that light is growing faster than the light can cross it, rather like a person walking forward on a treadmill that is moving backward faster than they can walk, so that, despite their forward motion, they find themselves moving backward relative to the room around them. The existence of this horizon means that there are regions of the universe, vast regions containing countless galaxies and stars and worlds, from which no signal will ever reach us, no matter how long we wait, no matter how sensitive our instruments become, no matter how patient our descendants might be in their listening. But the situation is actually more troubling than this static picture suggests, because in 1998, two independent teams of astronomers made a discovery that would earn them the Nobel Prize in Physics in 2011 and would fundamentally alter our understanding of cosmic destiny. These teams, one led by Saul Perlmutter and the other led jointly by Brian Schmidt and Adam Rees, We're observing a particular type of stellar explosion called a Type Ia supernova, which occurs when a white dwarf star accumulates matter from a companion until it reaches a critical mass and detonates in a thermonuclear explosion of remarkable uniformity. Because these explosions are so consistent in their intrinsic brightness, they serve as what astronomers call standard candles, objects whose true luminosity is known, so that by measuring how bright they appear from Earth, we can calculate how far away they must be. What the teams expected to find was that the expansion of the universe was slowing down over time, that the gravitational attraction of all the matter in the cosmos was gradually decelerating the outward rush of galaxies, like a ball thrown upward that slows as it rises before eventually falling back. What they found instead was the opposite, that the expansion of the universe is accelerating, that space is stretching faster and faster with each passing cosmic moment, as though the ball thrown upward were not slowing but speeding up as it rose, accelerating away from the thrower with ever-increasing velocity toward the sky. The cause of this acceleration remains one of the deepest mysteries in physics, and we give our ignorance a name by calling it dark energy, a term that captures how little we understand about its nature while acknowledging its observable effects. Dark energy appears to be a property of space itself, a kind of inherent pressure or tension in the fabric of the vacuum that drives space to expand. And unlike ordinary matter or energy, which becomes more dilute as space expands, dark energy appears to maintain a constant density, so that as new space is created by expansion, more dark energy comes into existence along with it, driving further expansion in a kind of cosmic positive feedback loop. The implications of this acceleration for the future of the observable universe are sobering, and they bear directly on the question of cosmic isolation that concerns us here. Because the accelerating expansion means that the cosmological horizon is not static but is actually shrinking, that regions of space currently within our observable universe will eventually cross the horizon and become forever invisible to us, their light redshifted beyond detection, their matter carried away into realms from which no message can ever return. In 2007, the physicists Lawrence Krauss and Robert Scherer published a paper with the evocative title "The Return of a Static Universe and the End of Cosmology," in which they explored what this accelerating expansion will mean for any civilizations that might exist in the far future. Their conclusion was remarkable and melancholy, that within a few 100 billion years, the acceleration of cosmic expansion will have carried every galaxy beyond our local group across the cosmological horizon, leaving our distant descendants in a universe that appears to contain only the merged remnant of the Milky Way and Andromeda galaxies, a single island of stars floating in an otherwise empty and static void. The cosmic microwave background radiation, that faint echo of the Big Bang that currently permeates all of space, will have been redshifted to wavelengths so long that it will be utterly undetectable. The distant galaxies that currently speckle the night sky in deep field photographs will have vanished entirely, their light no longer able to reach us. And so a future civilization arising in that era, even one possessed of the most sophisticated instruments and the most brilliant physicists, would have no evidence that the universe had ever been any different than it appeared, no way to deduce that cosmic expansion was occurring, No hint that their island of stars was once part of a vast cosmic web of hundreds of billions of galaxies. They would look out at what appeared to be an eternal, unchanging, empty cosmos, and they would have no way of knowing that they were wrong. This is relevant to our discussion because approximately 94% of the galaxies that are currently visible in our telescopes will eventually fade beyond our cosmological horizon, carried away by the relentless acceleration of cosmic expansion until their light can no longer reach us. These are not merely distant abstractions, but real collections of hundreds of billions of stars, many of them likely orbited by planets. Some of those planets perhaps hosting conditions suitable for life. And once they cross the horizon, they are not merely far away in any ordinary sense. They are causally disconnected from us, existing in a region of space-time from which no information, no signal, no influence of any kind can ever propagate to our region. This is the loneliness of light cones. The recognition that the cone of past events that can influence us and the cone of future events that we can influence are finite, bounded structures, and that vast regions of the universe lie permanently outside these cones, as inaccessible to us as if they existed in a separate reality entirely. Now, we must consider what this means for the question of whether another version of you might exist somewhere in the cosmos. Even if we were to grant, for the sake of contemplation, that the universe is infinite and contains somewhere another configuration of matter that exactly replicates your physical structure, that hypothetical copy would almost certainly lie beyond our cosmological horizon, either now or eventually, carried away by the expansion of space into regions forever beyond our reach. There could be no meeting between you, no exchange of messages, no verification that such a copy exists, no interaction of any kind. The two of you would be as separated as if you existed in entirely different universes, which, in a meaningful physical sense, you would. The mathematical possibility of such a copy, if it even is a coherent possibility, would remain forever purely theoretical, an abstraction that could never be confirmed or falsified, a philosophical curiosity with no bearing on your lived experience or your practical uniqueness. This brings to mind a question that has puzzled scientists and philosophers for decades. First articulated clearly during a lunch conversation at Los Alamos National Laboratory in 1950 by the physicist Enrico Fermi. The question, which became known as the Fermi paradox, is simply this: that if the universe is vast and old and filled with stars and planets, and if life and intelligence arise with any reasonable probability, then where is everyone? The apparent silence of the cosmos, the absence of clear signals or visitations from other civilizations, has prompted many proposed explanations over the years, ranging from the possibility that intelligence is vanishingly rare to the possibility that civilizations tend to destroy themselves before they become capable of interstellar communication. But the loneliness of light cones suggests another dimension to this silence, that even if the universe teems with intelligent life, even if civilizations exist around billions of stars in billions of galaxies, the expansion of space ensures that most of them are and will remain forever beyond our horizon, their signals unable to reach us, their existence undetectable by any instrument we could build, their histories unfolding in regions of space-time that are as separate from ours as parallel universes in a science fiction story. The Victorian physicist Lord Kelvin speculated as early as 1852 about what he called the universal tendency in nature toward the dissipation of mechanical energy, what we now describe more formally as the second law of thermodynamics and its implication for the far future of the cosmos. This speculation pointed toward what later became known as the heat death of the universe, or the Big Freeze, a state in which the universe has expanded so much and entropy has increased so far that no more work can be done. No more energy can be extracted to power any process, and everything reaches a final uniform temperature just barely above absolute zero. In this ultimate future, the stars will have burned out. The black holes will have evaporated through Hawking radiation. The protons themselves may have decayed, and the universe will be a cold, dark, empty expanse of radiation cooling towards absolute zero, with no structure, no complexity, and no possibility of life or thought. This is the loneliest destiny imaginable. A cosmos that ends not with drama, but with the quietest of whimpers. A long, slow fade into eternal stillness. And so we arrive at a recognition that is perhaps melancholy, but also strangely peaceful. That each conscious being exists in profound cosmic solitude. Not because there is anything defective or incomplete about existence, but because this is simply the nature of reality given the physics of space and time. The light cone that contains your past and future is yours alone, shaped by the particular events that have influenced you and the particular events that you might influence, and no other being, no matter how similar to you in configuration, shares that same light cone. Your experience of the universe, your particular angle of vision on the cosmos, your specific thread through the web of causation, these are unique to you in a way that no amount of cosmic repetition or infinite space could change. Even if somewhere beyond the horizon there exists a pattern of matter that mirrors your own, that pattern would have its own light cone, its own causal history, its own unrepeatable thread through existence. This is not a tragedy, but simply a fact, like the fact that water freezes at 0 degrees, or that light travels at approximately 300,000 kilometers per second. The loneliness of light cones is built into the structure of space-time, a consequence of the finite speed of light and the expansion of space, and it is no more cause for distress than any other feature of the physical world. Indeed, there is a certain comfort in recognizing that your uniqueness is not merely a matter of probability or complexity, but is physically guaranteed by the causal structure of the universe. That the cosmos itself ensures that you are the only version of yourself that will ever exist within the bounds of what exists for you. The horizon that separates you from hypothetical copies is not a barrier to be overcome, but a feature of reality that defines the very meaning of existence and identity. And with that recognition, we might let the thought settle gently, like dust motes drifting through a beam of afternoon sunlight, noting that the universe, for all its vastness, is a quieter and more intimate place than it sometimes appears, and that each conscious being occupies a small, bright region of space-time that is entirely their own, irreplaceable and complete. In the year 1948, in a quiet office at Bell Telephone Laboratories in New Jersey, a mathematician named Claude Shannon published a paper that would change how we understand everything, from the signals traveling through telephone wires to the nature of human identity itself. The paper was titled A Mathematical Theory of Communication, and it introduced a concept so fundamental that we now take it almost entirely for granted, though at the time it represented something genuinely new under the sun. Shannon proposed that we could measure information, that we could quantify it as precisely as we measure temperature or weight or distance, and that this measurement would tell us something real about the structure of the universe itself. He called his unit of measurement the bit, a contraction of binary digit, and he showed that every message, every signal, every pattern that distinguishes one thing from another could be expressed in these simple units of yes or no, 1 or 0, this or that. What Shannon understood, and what we are only now beginning to fully appreciate, is that information is not merely something we communicate about reality, but is in some fundamental sense what reality is made of, the underlying fabric from which all distinguishable things are woven. To understand why you are unrepeatable, we must first understand what it means to describe something completely, to capture every detail that makes it what it is and not something else. When Shannon developed his theory, he was thinking primarily about practical problems, about how to send messages efficiently through noisy channels without losing their meaning. But the implications of his work extended far beyond telephone lines and telegraph wires. He showed that the amount of information needed to describe a system depends on how many different states that system could possibly occupy, on how many ways it could be arranged while still being a valid configuration of whatever it is. A coin resting on a table requires only one bit to describe, because it can only be heads or tails, this way or that way. And once you know which it is, you know everything there is to know about its orientation. But a human being, even considered only as a physical system, as an arrangement of atoms and molecules and quantum fields, requires an almost incomprehensibly larger amount of information to describe, because the number of ways those components could be arranged while still constituting a coherent physical object is vast beyond ordinary imagination. This brings us to a discovery made in 1972 by a young physicist named Jacob Bekenstein, who was working at Princeton University on one of the strangest objects that physics predicts, the black hole. Bekenstein was troubled by what seemed like a contradiction between black holes and the fundamental laws of thermodynamics, the laws that govern heat and energy and the flow of processes through time. Specifically, he was concerned about entropy, which is a measure of disorder or uncertainty, a way of counting how many microscopic arrangements could produce the same macroscopic appearance. The second law of thermodynamics insists that entropy can never decrease in a closed system, that disorder always increases, or at best, stays the same. But black holes seem to violate this principle by swallowing matter and apparently destroying all the information about what that matter had been. Bekenstein proposed something remarkable, that black holes themselves must have entropy, that they must somehow store information about everything that falls into them. And he showed that this entropy is proportional not to the volume of the black hole, but to the area of its surface, to the two-dimensional boundary that separates inside from outside. This was strange and unexpected, because we normally think of information as filling a space, as being distributed throughout a volume, not as being somehow painted on a surface like words on a page. Bekenstein's insight lay dormant for some years. appreciated by specialists, but not yet understood in its full implications. Until the 1990s, when two physicists, Leonard Susskind at Stanford and Gerard 't Hooft in the Netherlands, developed what came to be known as the holographic principle. They recognized that what Bekenstein had discovered about black holes might be true about the universe as a whole, that there is a fundamental limit to how much information can be contained in any region of space, and that this limit is determined by the area of the boundary surrounding that region, not by its volume. This is deeply counterintuitive, because it suggests that the three-dimensional world we perceive is in some sense a projection of a two-dimensional encoding. Much like a hologram on a credit card encodes a three-dimensional image on a flat surface. The holographic principle tells us that information is finite, that there is an ultimate graininess to reality, a smallest unit of distinguishability below which the universe simply cannot make finer distinctions. And this means that every physical system, including you, can in principle be described by a definite, though enormously large, number of bits. So how many bits would it take to describe a human being completely, down to the last quantum detail? The physicists who have calculated this estimate the answer at roughly 10 to the power of 28 bits, a number so large that writing it out in full would fill many pages with zeros. This is the amount of information encoded in the positions and momenta and quantum states of all the particles that comprise your body at this very moment. The exact configuration of every electron and quark and photon that participates in the symphony of interactions that constitutes your physical existence. 10 to the 28th bits is vastly more information than all the data humanity has ever recorded, more than all the books ever written and all the photographs ever taken and all the conversations ever held, by a margin that defies meaningful comparison. And this information is not static but constantly changing, flowing and flickering as particles interact and quantum states evolve, so that the complete description of you at this moment is different from the complete description of you a moment ago, and both are different from the description that will be accurate a moment hence. Now we must consider whether this pattern, this particular arrangement of 10 to the 28th bits that constitutes you reading these words, could ever be duplicated, whether somewhere in an infinite universe or in the long stretches of future time, there might exist another arrangement exactly the same. The answer, surprisingly, comes from the deepest principles of quantum mechanics, from a result published in 1982 by William Wouters and Wojciech Zurek, a theorem known as the no-cloning theorem. What Wouters and Zurek proved is that quantum states cannot be perfectly copied, that there is no physical process that can take an arbitrary quantum system and produce an exact duplicate of it without disturbing the original. This is not a matter of technological limitation, not something that might be overcome with cleverer devices or more precise instruments, but a fundamental feature of how quantum mechanics works, a consequence of the linearity of the equations that govern quantum evolution. You cannot Xerox a quantum state because the very act of gathering enough information to make the copy would unavoidably alter the original, would collapse the delicate superpositions and entanglements that give the state its particular character. This has profound implications for identity. Because you are not merely a classical arrangement of atoms like beads on strings, but a quantum system of breathtaking complexity, a pattern of correlations and superpositions that extends across billions upon billions of particles. The no-cloning theorem tells us that this pattern cannot be duplicated, that there is no way, even in principle, to create a second version of the quantum state that constitutes you at this moment. And if your current state cannot be copied, then it follows that it will never exist again. Because once it has changed, once the relentless evolution of quantum mechanics has carried it into a new configuration, the old configuration is gone forever, not merely forgotten or unrecorded, but genuinely non-existent, removed from the inventory of things that are. In the year 2000, the physicist Seth Lloyd, working at the Massachusetts Institute of Technology, published a paper in the journal Nature that offered a remarkable perspective on these ideas. Lloyd proposed that we should think of the universe itself as a kind of quantum computer, a vast information processing system in which the laws of physics are the program and the state of all the particles and fields is the data being processed. In this view, every physical process, from the collision of galaxies to the firing of neurons in your brain, is a computation, a transformation of information from one configuration to another according to the rules encoded in the fundamental equations. What Lloyd showed is that the universe has performed a finite number of computational operations since the Big Bang, a number that can be estimated from the age of the universe and the energy available for computation. And this means that only a finite number of configurations have ever been realized. Only a finite number of information states have ever existed. The universe has not had time, and may never have time, to explore all possible arrangements, which means that most conceivable patterns will never occur even once, let alone twice. There is another dimension to consider, one that touches on the nature of consciousness itself, and here the science becomes more speculative, but no less fascinating to contemplate as you drift towards sleep. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff have proposed a theory called orchestrated objective reduction, which suggests that consciousness arises from quantum processes occurring in microscopic structures within neurons called microtubules. Whether or not this particular theory is correct, and many scientists remain skeptical, it raises the possibility that the experience of being you, the inner felt quality of your existence, depends on quantum effects that the no-cloning theorem would prevent from being duplicated. If consciousness involves quantum coherence in some essential way, then the unrepeatable nature of quantum states applies not only to the physical configuration of your body, but to the subjective experience of being who you are, to the inner light of awareness that accompanies your passage through each unrepeatable moment. So we arrive at a gentle but profound conclusion, one that follows not from mystical intuition or poetic fancy, but from the careful mathematics of information theory and quantum mechanics and the physics of entropy. The complete description of you at this moment, the full quantum specification of every particle and field that constitutes your physical existence, has never been instantiated before in all the history of the universe, and will never be instantiated again in all its future. You are not merely rare, but literally unique. Not an unlikely event, but an unrepeatable one. A pattern of information that the cosmos has expressed exactly once and will never express again. The holographic principle tells us that your information content is vast but finite. The no-cloning theorem tells us it cannot be copied, and the quantum evolution of the universe tells us it will not recur. And together these facts establish your uniqueness, not as a pleasant sentiment, but as a consequence of fundamental physics. And perhaps there is something restful in this realization, something that allows the mind to settle rather than race. You need not worry about alternate versions of yourself making different choices, about duplicates in distant galaxies living lives you might have lived, because the laws of physics do not permit such duplication. Do not allow the pattern that is you to be reproduced or repeated. The arrangement of information that constitutes your experience of listening to these words, of feeling whatever you are feeling, of being wherever you are being, is occurring for the first and only time. A singular flowering of complexity in an unimaginably vast but not infinitely various universe. This does not make your existence fragile or frightening, but simply makes it what it is. A genuine original, an unrepeatable expression of possibility, which perhaps you can carry with you into sleep as a quiet and comforting fact. And so we return now to the stars, those distant lights that have watched over sleeping creatures for as long as there have been eyes to see them. And we find ourselves once again considering the vast cosmic perspective, not with any sense of smallness or insignificance, but with a quiet and abiding wonder at what it means to exist at all in such an immense and ancient universe. A universe that has been unfolding for nearly 14 billion years and will continue to unfold for timescales so vast that our ordinary numbers lose all meaning when we try to describe them. On the 14th of February in 1990, a spacecraft called Voyager 1, which had been traveling outward from Earth for more than 12 years by that point, turned its cameras back toward home one final time before those cameras were switched off forever to conserve power for the long journey ahead. And from a distance of approximately 3.7 billion miles, it captured an image that would become one of the most significant photographs ever taken. Though significant is perhaps too strong a word for something so profoundly humble. An image showing Earth as nothing more than a tiny point of light, a pale blue dot suspended in a beam of scattered sunlight, measuring just 0.12 pixels across in the original frame, barely distinguishable from the noise and artifacts of the camera itself, and yet unmistakably there, unmistakably home. The astronomer Carl Sagan, who had championed the idea of taking this photograph and who understood perhaps better than most the importance of seeing ourselves from such a distance, reflected on this image with characteristic gentleness and clarity, noting that everyone who had ever lived, every human being who had ever loved or grieved or wondered at the night sky, every empire that had risen and fallen, every mother who had held a sleeping child, every scientist who had puzzled over the nature of reality, all of them had lived out their entire lives on that tiny mote of dust suspended in a sunbeam. And there is something both humbling and strangely comforting in this perspective, knowing that all of our joys and sorrows, all of our grand ambitions and quiet moments of peace have taken place on a world so small that from sufficient distance it nearly vanishes entirely. But what strikes us now, as we drift among these singular stars with our minds settling toward sleep, is not merely the smallness of our world, but its absolute and irreplaceable uniqueness. The fact that in all the vastness of space that Voyager 1 traversed, and in all the depths of cosmos that our more recent telescopes have revealed, we have found nothing quite like Earth, nothing quite like the particular arrangement of water and rock and atmosphere and life that makes our pale blue dot what it is, and certainly nothing like the billions of unique individuals who have called it home, each one of them experiencing existence in their own unrepeatable way. The James Webb Space Telescope, which left Earth on Christmas Day of 2021 and now orbits the Sun at a point roughly 1 million miles from our planet, has opened windows onto the universe that previous generations could scarcely have imagined, showing us galaxies as they appeared 13.4 billion years ago, when the universe itself was young and the first stars were only beginning to illuminate the cosmic darkness, light that has been traveling toward us for longer than Earth has existed, longer than our sun has burned, crossing such incomprehensible distances that the very fabric of space has stretched during its journey, shifting its color toward the red end of the spectrum in ways that tell us precisely how ancient and how distant these sources truly are. And what strikes the astronomers who study these images, what emerges from every deep field observation and every careful analysis of distant galaxies and nebulae and stellar nurseries, is not repetition, but rather endless variation. Not copies, but originals. Not duplicates, but singular expressions of the physical laws that govern our universe, playing themselves out in unique configurations across the breadth of space and time. And nowhere in all these observations, nowhere in the thousands of exoplanets we have catalogued or the billions of galaxies we have imaged, have we found anything that repeats exactly? Anything that suggests the universe is in the business of making copies rather than continuously creating new and unrepeatable arrangements of matter and energy and structure. The astronomer Jill Tarter, who has dedicated much of her life to the search for extraterrestrial intelligence through the SETI Institute, listening with radio telescopes for any sign of technological civilizations beyond our own, has reflected on what it means that after decades of careful searching, the cosmos remains profoundly silent, or at least profoundly quiet in terms of the artificial signals we might expect from beings like ourselves. And while this silence might seem lonely or discouraging to some, there is another way to understand it. A way that emphasizes the apparent rarity and preciousness of minds capable of asking such questions at all. The possibility that consciousness, that self-awareness, that the ability to wonder about one's place in the universe might be so extraordinarily unlikely that it represents not a commonplace occurrence repeated endlessly across the stars, but rather a precious and unusual flowering that deserves our deepest appreciation wherever and whenever it occurs. We do not yet know, of course, whether we are alone in the universe, whether other minds are out there contemplating their own existence and perhaps searching for us just as we search for them. But what we can say with some confidence is that even if the universe contains other conscious beings, this does nothing to diminish the uniqueness of any particular consciousness, just as the existence of other snowflakes does nothing to diminish the singular and unrepeatable pattern of any individual crystal falling through a winter sky. Each mind, wherever it might arise, would be its own irreplaceable perspective, its own window onto existence, its own way for the universe to know itself. The astronauts who have had the privilege of seeing Earth from space often report an experience that has come to be known as the overview effect, a profound shift in awareness that comes from viewing our planet as a whole, as a fragile and beautiful sphere hanging in the blackness of space without the political boundaries and national divisions that seem so important from the surface. And one of the most eloquent descriptions of this experience came from Edgar Mitchell, who traveled to the moon aboard Apollo 14 in February of 1971, and who later described the epiphany he experienced while gazing back at Earth during the return journey. A sudden and overwhelming sense that the universe was in some fundamental way intelligent and purposeful. That consciousness was not separate from the cosmos, but rather an integral part of it. That the molecules in his body, and the molecules in the spacecraft, and the molecules in the distant stars were all connected in ways that transcended ordinary understanding. And this brings us to a perspective that may be helpful as you drift towards sleep. A way of understanding your own existence that neither inflates your importance beyond reason nor diminishes it into meaninglessness. A middle path that recognizes both the vastness of the cosmos and the preciousness of the particular. And this perspective, expressed perhaps most beautifully by the philosopher Alan Watts, is simply this: that you are not a stranger in the universe, not an accident or an anomaly or an outside observer looking in, but rather the universe itself experiencing itself in a particular and unrepeatable way. The cosmos grown conscious of itself through the temporary arrangement of atoms that currently constitutes your body and your brain and your sense of being someone who exists. The atoms that make up your body were forged in the hearts of ancient stars that burned and died long before our solar system formed. Carbon and oxygen and nitrogen and all the heavier elements that life requires were created through nuclear fusion in stellar cores or scattered across space in supernova explosions. And these star-forged atoms eventually found their way into the cloud of gas and dust that collapsed to form our sun and planets. And eventually into the food you have eaten and the air you have breathed and the water you have drunk, until they became part of you, arranged in this particular configuration that somehow gives rise to consciousness, to awareness, to the experience of being you. And this arrangement has never occurred before in all of cosmic history and will never occur again in precisely the same way. You are not diminished by your uniqueness, but elevated by it. Not made smaller by the knowledge that you are a one-time occurrence, but made infinitely precious. A brief and unrepeatable flowering of the universe's capacity to know itself, to feel, to wonder, to love, to rest. And when this particular arrangement of atoms eventually disperses, as all arrangements eventually must, the universe will not have lost a copy or a duplicate of something that exists elsewhere. It will have lost something that existed only once and only here and only now. Something irreplaceable in the strictest possible sense of that word. And the universe will continue. Of course, for timescales that make our brief human lives seem vanishingly small. Current physics suggests that the cosmos will continue evolving and changing for spans of time almost impossible to comprehend. That stars will continue to form and burn and die for trillions of years to come. And that, even after the last stars have faded and the last black holes have evaporated through Hawking radiation, the universe will persist in some form for perhaps 10 to the power of 100 years, a number so large that writing it out would require more digits than there are atoms in the observable universe. And throughout all of this unimaginable expanse of future time, the particular arrangement of matter that is you, that is experiencing these words right now, that is drifting towards sleep in this particular moment of cosmic history, will never occur again. But there is nothing sad in this, nothing to mourn or resist, only a quiet recognition of the preciousness of what is. The unrepeatable gift of consciousness experiencing itself in this particular form at this particular time. And as you settle deeper into relaxation, as your breathing slows and your thoughts begin to soften around the edges, you can carry with you the gentle knowledge that you are cosmically singular, that the universe has never before and will never again arrange itself in precisely the pattern that you represent, and that this makes your experience of existence, this very moment of drifting towards sleep while contemplating the stars, something genuinely unprecedented in all of space and time. The stars will continue their slow wheeling across the night sky, as they have for billions of years and will for billions more. And each of them is unique as well, each one a slightly different mass and composition and age and luminosity. No, two exactly alike in all the hundreds of billions of stars in our galaxy alone, and each of the planets that orbit those stars, and each of the moons that orbit those planets, and each of the rocks and ice crystals and dust grains that drift through the interstellar medium, all of them singular, all of them unrepeatable. And you are part of this cosmic tapestry of uniqueness, not separate from it, but woven into it. Your consciousness, one of the rarest and most precious threads in a universe that seems to specialize in creating things that have never existed before. And so, as sleep approaches, as your awareness begins to loosen its grip on the waking world, you can rest in the knowledge that you are enough, that you are exactly what you need to be, that there is no other version of yourself that you should have been or could have been. No template or ideal against which you fall short. Only this singular and unprecedented expression of cosmic creativity that is you, right now, in this moment, breathing slowly and peacefully as the stars wheel overhead in their ancient patterns, and the universe continues its long, slow journey toward destinations we cannot imagine, carrying you with it as one of its most precious and unrepeatable creations. A brief arrangement of star-forged atoms that somehow learned to wonder at its own existence. And that is now, quite rightly, drifting off to sleep.